Right, in this video, we are going to talk about forces, that is types of forces, effects of forces, equilibrium. Right, so that's what we're going to be talking about. So it's starting with types of forces. The first type of force we're going to consider here is upthrust. When an object is in a fluid, such as water, it will displace a certain amount of the fluid. This produces an upward force on the body, and the apparent weight of the body is therefore less in the fluid than it would be in a vacuum. So if you submerge, say, this stone in water, the water produces this upthrust, okay, which pushes it upwards. So you now have weight and upthrust. The magnitude of this upward force or the upthrust depends on the volume of the body. That is, the more fluid that is displaced, the greater the upthrust. It also depends on the density of the fluid. The greater the density, the greater is the upthrust. Origins of the upthrust. Now, upthrust arises from the pressure difference which the fluid exerts between the lower and the upper surface on the object, as shown. So remember, pressure increases with depth. We said P is equal to rho GH. So it means looking at this depth here at the bottom, looking at the depth at the bottom, pressure will be more because the height will be more coming from the surface. We're coming from the surface going down. At this depth here, there's less pressure than at the depth at below. So we're going to find the pressure at this depth, then subtract the pressure at this depth, and then we multiply by the area to get the force, because pressure is equal to force over area. Force will be pressure times area. So upthrust arises from the pressure difference which the fluid exerts between the lower and the upper surface on the object. So as shown on the diagrams there, the force on the upper face of the cylinder is H rho G times A, that is pressure times area, right? And then the force on the lower will be equal to that H plus this L, that will be the depth, times GHA. That is, all this will be the pressure, which is H rho G times the area. So the difference in the force, which is the net upward force, will be equal to LPGA, because the H will go away. The volume of the liquid displaced by the cylinder will be LA. The weight of the liquid displaced will be LA rho G. Okay, this because we know that W is equal to mg, so which is equal to rho Vg. Okay, so rho Vg will be our weight. So rho Vg, La is volume, then we've got rho G there. The net upward force on the cylinder is equal to the weight of the fluid displaced by it. This is the statement known as Archimedes' principle. When a body is wholly or partially immersed in a fluid, there is an upthrust which is equal to the weight of the fluid which is displaced. So Archimedes' principle, I'll repeat, when a body is wholly or partially immersed in a fluid, there is an upthrust which is equal to the weight of the fluid displaced. If the weight of an object is equal to the upthrust, it will float. This is known as the principle of flotation. So which means that, let's move on. A ship floats because the internal volume displaces a large volume of water, which produces sufficient upthrust to balance the weight of the ship. The fluid may be a liquid, such as water, or a gas, such as air. So anything between a liquid or a gas is a fluid. Anything that can flow is a fluid. Now, we're going to talk about these examples. Examples. The first one, a 20 kg spherical hollow steel buoy of volume 0.06 cubic meters is tethered to the bottom of a fast-flowing river by a cable, so that the cable makes an angle of 40 degrees with the vertical. Calculate the tension T in the cable. Now, if it makes an angle with the vertical of 40, which means if you are resolving to the vertical, it is a cos. So we can say that the upthrust will be equal to the weight plus the T cos 40, right, to the vertical. So we can say upthrust is equal to 20G plus T cos 40, where G is the gravitational field strength. But upthrust is equal to rho Vg, like I said, rho Vg. Rho is 1000, which is the density of water. And then 0.06 is the volume, and then G. So rho Vg is upthrust. Then we are going to equate, therefore, rho Vg is equal to 20G plus T cos 40. Now, making T the subject will give you T is equal to 511 newtons. Please work it out and then comment if you do not understand. Okay, that's it. That's just a repetition of it. Then we have the second one. Wow, again, that's the same one. I don't know what's going on with my document. Now the second one is about a hot air balloon. A hot air balloon has a volume of 200 cubic meters and it hangs in air. If the density of the hot air is 0.8 kgs per cubic meter and that of the cool air outside the balloon is 1.2 kgs per cubic meter, what is the biggest load it can support if the fabric of the balloon and the basket have a total mass of 60 kgs? Take G to be 9.8 meters per second squared. Now, first of all, you need to find the weight of the balloon and the basket. So it's going to be mg, which is 60 kgs times g, which gives you 588 newtons. And then upthrust will be equal to the weight of the air displaced. And remember, that is our rho Vg, which is going to be V is that one. Rho is 1.2, which is this is the density of the air outside the balloon, which is going to be displaced by the balloon, times G, which gives you 2,352 newtons. And then the weight of the hot air in the balloon is equal to rho Vg again, which is 200 cubic meters, because we assume that the hot air occupies that volume. So 200 times the density of the hot air, which is 1.2. It's going to 200 times 0.8, the density of the hot air, and then times 9.8, giving you 1,568. So which means the total weight of the balloon and the hot air will be equal to the 1,568 of the hot air plus the weight of the balloon and the basket, which is 588 newtons. So you get a total of 2,156 newtons. Therefore, the additional load that can be supported by the balloon will be equal to the 2352, which is what is going to be displaced, the coordinate that's going to be displaced. Then you subtract the total that we found there, which is equal to 196 newtons. Then frictional and viscous forces. Friction is the force that opposes motion or probable motion produced between surfaces or fluids and surfaces. Frictional forces are dissipative in nature because energy is required to overcome them. The work done to overcome friction is changed into heat. Friction always acts along a surface, not at an angle to it, and is in the opposite direction to the direction of the motion or the probable motion. There is static friction and sliding friction. Static friction is the friction between the surfaces when the object is not moving, but just gripping. Then sliding or dynamic friction will be the friction between the surfaces which are sliding past each other. Usually, sliding friction is less than static friction, but for theoretical purposes, that is theoretically, but for practical purposes, the difference is very negligible. Friction is caused by uneven surfaces. The surfaces of objects have humps and hollows which catch each other. Molecules in the two surfaces which tend to stick together when pressed. When an object moves in a fluid, the frictional force is called a viscous force. Air resistance acting on a moving car or an object falling in a liquid are examples. In laminar flow, that is when each particle of the fluid follows a smooth path and the path of each particle do not cross each other, the viscous force increases proportionally with speed. Above critical speed, the fluid flow becomes irregular and turbulent. The viscous force increases proportionally with the square of the speed. Similarities between frictional force and viscous forces. Both oppose motion. Both occur due to attractive forces between molecules, and both are dissipative in nature. The differences between frictional forces and viscous forces. Frictional forces act along the surface in contact between the two objects, whereas viscous forces act between a solid and a fluid, or between a fluid and a fluid, or solid. Viscous forces increase with relative speed between two surfaces, whereas frictional forces are not affected by relative speed between the two surfaces. Then the third difference, viscous forces do not exist when there is no relative motion, whereas frictional force exists even when the object is at rest. Right, moving on to attaining effects of forces. I think you've covered this one in lower forms, but we're going to cover it again. We know that the center of gravity of a body is that single point at which this entire weight of the body can be considered to act. Please watch this definition. It's very important. It is considered to act, or appears to act, or seems to act. Okay, the single point at which the entire weight of the body appears to act, seems to act, or is considered to act. Any of those synonyms. For a uniform body, the center of gravity is at the geometric center. An object balances if it is supported at the center of gravity, CG. If it is supported at another point, the moment of its weight causes it to turn. We call that a destabilizing moment that is formed. Now, turning effects of forces. A turning effect of a force is this moment, and the moment of a force about any point is defined as the force times the perpendicular distance of the line of action of the force to the pivot. We're going to use the symbols T, F, and D. T is the moment, F is the force, D is the perpendicular distance of the line of action of the force to the pivot. The unit of moment of a force is Newton meters, and they can be clockwise or anti-clockwise. So a clockwise moment is one which is a clockwise effect about the pivot. So we've got a pivot here. This force is pulling down, causing this one to move in a clockwise direction. And then if the force is up, like the second case, it is a tendency of making it go the other way, which would be an anti-clockwise moment. Now, to get the clockwise moment for the first case here, we say the force times the perpendicular distance, so 90 degrees there, but to D, so that becomes FD. Now, for this one, to get the clockwise moment, we are going to resolve this one so that it is perpendicular to the distance. Okay, perpendicular to the distance. So in that case, we are going to get let's see, it's going to be F. If we have a cos here, let's just say this is a cos. Let's just say this is theta, angle theta here. It's going to be F sine theta times D. Okay. Or we could just say F times this perpendicular distance. When we found it, perpendicular distance that closes this triangle will be that. Now, the principle of moments states that when a body is in equilibrium, the sum of the clockwise moments about any point must equal the sum of the anti-clockwise moments about the same point. Now, we're going to look at examples that regard this moment of a force. Now, the first example, a uniform meter rule supports 4.5 newtons of weight at its 100 millimeter mark. The rule is balanced horizontally on a horizontal knife edge at the 340 millimeter mark. Sketch the arrangement and calculate the weight of the rule. Now, the answer to this one is 6.75. Now, let's try and work it out. Let's see. Right, so the uniform meter rule, you can draw it like this, and then it's supporting a weight. So this is from 0 to 100 millimeters. So this will be 100 centimeters, which is 1,000 millimeters. So if you had to put it in millimeters, it would be 1,000 millimeters. So 100 millimeters will be somewhere here. So it says supports a weight that's 4.5 newtons there. It is 100 millimeter mark. The bow balance horizontal on a knife edge. It is 340 millimeter mark. So 340 millimeters will be there. Okay. Then okay, let's just extend this one so that we have the center of mass. Remember, it acts at the center. That will be the 500 millimeter mark. And then we'll have a 1,000 millimeter mark right at the end here. And we are told that the weight of is 4.5 newtons. Then what they do, they want to sketch the arrangement and calculate the weight of the rule. Sorry, so we've got the weight of the rule here, not 4.5. Sorry about that. Right, so we're going to consider the forces and the perpendicular distance from the pivot. Force and perpendicular distance from the pivot, that is. So this will be 340 minus 100, which should give you 240 there. And then this will be 500 minus 340. 500 minus 340, which is 160. So this distance is 160 millimeters. Right, so we can say applying the principle of moments, clockwise moments must equal anti-clockwise moments. So we're going to have W times 160. So 160 W should equal 4.5 by 240. So W is equal to 4.5. Let's raise it up so that you can see. So it will be 4.5 by 240 over 160. Right. That will be 6.75. So that's the weight of the meter. Okay. Then talk of a couple. Now, a couple is produced when two parallel forces of equal size act in opposite directions and have lines of action that do not coincide. You apply a couple when you turn a tap. Also when you are turning, when you are driving. When you do the push and pull method, you find that you form a couple. Torque is a measure of how much force acting on an object causes the object to rotate. So the torque of a couple is equal to one force multiplied by the perpendicular distance between the two forces. So one force times perpendicular distance. So remember, to have a couple, we should have the two forces equal, right? The two forces must be equal, but pulling in opposite directions. So if you say one force multiplied by the total distance between them, so that's 6. So 2 times 6 there will be equal to 12 Newton centimeters. Okay. Then for this one, it's going to be 2 times 8, which is 16 Newton centimeters. You could convert this into Newton meters again to get 0.12 Newton meters, or the 0.16 Newton meters in the second case. A torque of a couple does not depend on the position of the turning point. So as you can see from here, it's still a couple turns. So it's a couple whether this distance is less than this distance, it's still a couple. Whether this is equal, it's still a couple. But the lines of action must not coincide. Like I'm saying, if we have the 2 Newton force upwards on the same point here, it doesn't become a couple. So the two lines of force must not coincide. Right, so that is it. A couple tends to produce rotation only. Produces rotation only, no translational force. Then the next thing is forces in equilibrium. Forces in equilibrium. The equilibrium of a point object is achieved when two forces act on a point object. They could be at rest or moving at constant velocity. So if the two forces are equal and opposite each other, they are in balance. The resultant force is 0, and the point object is idealized. It is a mass, but is no size. So suppose you've got this one, you've got a push of the book on the table, then you've got a push of the table on the book. So that's a point mass there, it's shown in black. With 3 forces acting on a point object at O, the resultant is 0 only if the resultant of any of the 2 forces is equal and opposite to the third force. So that's the second one, you see from this table, from this one. Now if you resolve this one, that is, if you resolve T, yeah, okay, fine. If you can get these 2 forces, the resultant of these 2 forces should equal this force that is that's pulling in the opposite direction for it to be in equilibrium. Okay. To check if the resultant of the 3 forces is 0, each force can be resolved horizontally and along perpendicular lines, and then balancing the components along each line. So if you resolve this T, you get T cos theta to the horizontal, so to the vertical. So T cos theta to the vertical should equal W going down. Similarly, T sin theta should equal H. So for this to be in equilibrium. The vector sum of the forces adds up to 0. That is, the resultant of T and H is equal to and opposite to W. I've already talked about that. That's T plus H should be equal to minus W. If a point object is in equilibrium, there must be 0 resultant force. 0 resultant force. Vector triangle to represent coplanar forces in equilibrium. Forces in equilibrium mean that they are balanced. Coplanar forces act in the same plane. The triangle forces rule for three coplanar forces is in equilibrium states that if three forces acting at a point can be represented in size or direction by the sides of a closed triangle, then the forces are in equilibrium provided their directions can form a closed triangle. So if the three forces are in equilibrium, they form a closed triangle, and the forces must be facing the same direction. Okay, so T is facing that way, W down, H on the side. So they must be the same. The three forces drawn end to end form a closed triangle, and then the arrows are going in the same direction. Now, I'm going to end the video here, and then I'll do the example of the coplanar forces in the next video, and then we do conditions for equilibrium. So the last video is going to be a short one, just looking at examples as well as conditions for equilibrium. Signing out.